Welcome back for part 2 of chapter 82. Dalton was only a Columbus. The Vespuccis were still to come, and when they came, they would produce some delightful surprises and some terrifying shocks. Meanwhile, for a half-century, Dalton's indestructible solid atom served chemists well and was usefully elaborated. A French scientist, Gay-Lussac, showed that when atoms combined, it was not necessarily in the one-to-one fashion described by Dalton, but might be in some other arrangement of simple integers. An Italian chemist, Avogadro, 1776 to 1856, showed that equal volumes of gases at the same temperature and pressure contained equal numbers of molecules. And a Russian chemist, Mendeleev, proposed a suggestive, quote-unquote, periodic law of the elements. If elements were arranged in the order of increasing atomic weight, then groups of elements of similar characteristics would recur periodically. The dissolution of the indestructible solid atom would come from two sources, one familiar, the other quite novel, from the study of light and the discovery of electricity. Einstein himself described this historic movement as the decline of a mechanical view and the rise of a field view of the physical world, which helped put him on his own path to relativity, to new explanations and new mysteries. On the wall of his study, Albert Einstein kept a portrait of Michael Faraday, 1791 to 1867, and there could have been none more appropriate, for Faraday was the pioneer and the prophet of a grand revision that made Einstein's work possible. The world would no longer be a Newtonian scene of, quote, forces at a distance, end of quote, objects mutually attracted by the force of gravity inversely proportional to the square of the distance between them. The material world would become a tantalizing scene of subtle, pervasive fields of force. This was just as radical as the Newtonian revolution, and even more difficult for the lay mind to grasp. Like the Copernican revolution in astronomy, the field revolution in physics would defy common sense and carry the pioneer scientists once again into the mists of paradox. If Michael Faraday had been trained in mathematics, he might not have been so ready for his surprising new vision. The son of a poor blacksmith on the outskirts of London, Faraday had to earn his own way from an early age, and when wartime prices were high in 1801, he was said to have lived on a loaf of bread for a week. His parents were members of the Sandemanian Church, a small fundamentalist and ascetic Scottish Protestant sect, which, like the Quakers, believed in a lay clergy and opposed the accumulation of wealth. He attended Sunday meetings regularly and remained an elder until his last years. In his much-thumbed Bible, the most marked passages were in the book of Job. He had almost no formal education, quote, little more than the rudiments of reading, writing, and arithmetic at the common day school, end of quote. But at the age of 13, he luckily found employment with a friendly French émigré printer and bookbinder, a M. Ribot. At first, he delivered the newspapers that Ribot loaned out, and then he picked them up to be delivered again. Among the books that came to Ribot's shop for binding was The Improvement of the Mind by the hymn writer Isaac Watts, whose system of self-improvement Faraday followed by keeping the commonplace book that would eventually become his famous laboratory notebook. One day he received for rebinding the volume of the Encyclopedia Britannica, 3rd edition, 1797, that contained the article of 127 double-column pages on electricity by an erratic, quote, Mr. James Tytler, chemist, end of quote. Demolishing the prevailing one-fluid and two-fluid theories of electricity, Tytler proposed that electricity was not a material flow at all, but a kind of vibration, akin to light and heat. This tantalizing suggestion was the beginning of Faraday's pursuit of science. In 1810, he began attending public lectures offered by the City Philosophical Society and then Humphrey Davy's lectures at the Royal Institution. In December 1811, Faraday had impressed Davy by sending him the neatly bound and beautifully penned notes he had taken at Davy's lectures, along with his request for a post as his assistant. That October, Davy had been temporarily blinded by an explosion in his laboratory, and he now needed an amanuensis. I'm not sure what that word is. Davy hired Faraday for 1 guinea a week and the use of 2 rooms at the top of the institution with fuel and candles, laboratory aprons, and freedom to use the apparatus. At 20, Faraday found himself in the laboratory of one of the greatest chemists of the age, where he could experiment at will. A dream come true. Sir Humphrey and Lady Davy rounded off Faraday's education by taking him along on their tour of the continent in 1813-14, visiting France and Italy, meeting scientists, and sharing the talkative Davy's hopes and doubts. When Faraday returned to England in April of 1815, Davy had inoculated him against easy generalizations and had renewed his passion for experiment. Back in the laboratory, he tested heating and lighting oils and finally discovered benzene. He made the first known compounds of chlorine and carbon, which became ethylene, resulting from the first known substitution reaction. He pioneered in the chemistry of steel alloys. What eventually proved crucial in his life was the commission from the Royal Society that led him to produce a new heavy optical glass with a high refractive index, especially useful for experiments in polarized light. Faraday's sanguine temperament was reinforced by a happy marriage to the sister of someone he had met at the City Philosophical Society. Sarah Bernard never shared the scientific interests that kept him awake at nights, but she was happy to be, quote, the pillow of his mind, end of quote. In the new world of priority prizes, his early successes even aroused the jealousy of his famous mentor. In 1824, when Faraday was proposed as a fellow in the Royal Society for his feat of liquefying chlorine, Davy opposed his election and claimed that he himself was entitled to the credit. But Faraday was elected anyway. Davy had been intrigued by recent theoretical efforts to adapt Newton's ideas to the needs of the chemist in the laboratory. The most attractive of these was Boscovich's point-center theory, which had described the atom not as a tiny billiard ball of impenetrable matter, but as a center of forces. If the quote-unquote ultimate particles of matter should have this character, it might explain the interaction of chemical elements, their affinities, and the ways of making stable compounds. Boscovich had limited his radical suggestion to the chemical elements. When Faraday's passion for experiment was focused by chance on the uncharted realm of electricity, he was newly attracted by Boscovich's theory. In 1821, a friend asked Faraday to write for the Philosophical Magazine a comprehensive article explaining electromagnetism to the lay public. Current interest had been awakened when, just the previous summer, the Danish physicist Hans Christian Ørsted, 1777 to 1851, during the demonstration for an evening lecture, showed that a current-carrying wire would deflect a magnetic needle. Following Ørsted's clues, Faraday devised a simple apparatus of 2 beakers containing mercury, a current-carrying wire, and 2 cylindrical bar magnets. With this, he elegantly demonstrated electromagnetic rotation, proving both that a current-carrying wire would rotate around the pole of a magnet and that the pole of a magnet would rotate around a current-carrying wire. Perhaps Faraday began to suspect that somehow surrounding a current-carrying wire there were circular lines of force, and perhaps the forces of magnetism and of electricity were somehow convertible. At this point, it was lucky that Faraday was not a sophisticated mathematician, for then he might have followed the conventional path, like that taken by the French mathematical prodigy André-Marie Ampère, 1775 to 1836, and have tried to explain electromagnetism simply by a mathematical formulation of Newtonian centers of force. Faraday's naive vision saw something else. Without intending it, Faraday had already made the first recorded conversion of mechanical into electric energy. This was, of course, the crucial step toward the electric motor and the electric generator with all their transformations of daily life. Once again, a revolution in science would depend on the defiance of common sense. Surprising though it might seem, the power of a magnet, unlike the Newtonian force of gravitation, was not focused in a massy object emanating straight lines at a force at a distance. In numerous experiments after 1821, Faraday was beginning to glimpse a bizarre phenomenon and the possibility that the magnet and the electric current somehow created a field of force. Faraday, blessed with the amateur's naive vision, was not seduced by the revered Newton's mathematical formulae. Faraday's experiments over the next 25 years, from his first wires and magnets rotating in beakers of mercury to his grand prophetic outlines of a modern field theory, eventually would open the way to a new vision of the universe. Through it all, Faraday would be drawn by his simple Sandemanian faith in the unity and coherence of God's creation. And there we will stop for the end of part 2.